I will present my, my work in 45 minutes. So just before we start, un petit mot peut-être d'introduction en français. Donc merci à ceux qui sont là en présence ou sur le live qui est en ce moment sur Internet. Alors je ne sais pas combien vous êtes, je découvrirai ça à la fin. Donc je vais faire la présentation en anglais parce qu'on a un membre du jury qui est en anglais, ça va durer 45 minutes. Et ensuite il y aura la séance de questions-réponses qui se passera très bien en visioconférence. Donc, so I'm starting now, and I'm starting to explain you the context of my work. So I worked on iodine plasmas, both experimentally and numerically, with an application for electric propulsion. The context of this work is the new space. The new space movement that you probably know from its main representative, SpaceX, the launch company, is a movement characterized by new actors, new investors, new commercial opportunities, new risk approaches, or new investors. And many of those commercial opportunities are in the satellites industry. So the consulting companies are forecasting that over the next 10 years, more than 1,000 satellites per year will be launched. And those satellites need propulsion. They need propulsion to raise their orbits, they need propulsion to expand their lifetime, they need propulsion to avoid collisions, they need propulsion to deorbit so that they don't become a space debris, and they need propulsion to phase their constellation. That means you can use a single launch to bring your constellation in space and then make your own constellation with the thrusters of your satellites. The good propulsion for this is electric propulsion. Usually, people will use chemical propulsion. You have a fuel and an oxidizer that you burn together. This is freeing up some chemical energy, and you are using this chemical energy to accelerate your propellant outwards. Chemical propulsion is what happens when you decouple the power on the propellant. You will accelerate the propellant outwards with the power for someone else, for example, from solar panels. That means you can potentially achieve a bigger exhaust velocity, and a bigger velocity for a thruster means less propellant. So electric propulsion in low Earth orbit is characterized by a very low propellant consumption. The main propellant we are using for this today is xenon. Xenon is a noble gas, but it's scarce and expensive. For example, if you want to buy a small bottle of 1 liter at 11 bar, it's an equivalent of 60 grams, and you will pay 4,000 euros per kilogram. But that's not the worst. The yearly production is around 30 tons per year. It's a byproduct of the liquefaction of air. So if each of these 1,000 satellites per year will need 30 kilograms of propellant, and that's the case for the Starlink constellation, then you will run out of the yearly supply again. The community agreed that there is no perfect alternative as an atomic propellant. So the community, to look for a new propellant, has started looking into molecules. And they made a classification. They come with the idea that there is two families of propellant, of molecular propellant, that would be good propellants. It needs to be very easy or very hard to fragment. The idea is in both cases, when you turn on the plasma, you will directly come with a plasma that will look like an atomic plasma, whether it is from a diatomic molecules that directly dissociated and then make ions, or if your big molecules don't dissociate at all and become like a big atomic ion. In both cases, you don't have spent a lot of power ionizing your, dissociating your molecules, and that's what you are looking for. In the first category, easy to dissociate, I2 is the best candidate, iodine. In the periodic table, it's just next to xenon. So xenon is a noble gas. Here, it fits in a bottle, it's really stable. It doesn't make a lot of chemistry, that's why it's quite heavy, so that's why people liked it. Iodine is just next to it, but it's an halogen. It's much more reactive, but it has a lot of good things about it. The dissociation energy, because it comes as a molecule, is very low, 1.5 electron volts. It's lower than the typical electron temperature in the plasma, so it's good. And it comes in bottles like this. This is a screenshot from Amazon. And it comes as a solid pellets like this, that you can handle quite easily. That's good for engineers, for satellites. And as to turn them into a gas, you just heat them, and they turn into a gas. It's not something new. Like people have been studying iodine for a long time because, or despite its electronegativity. Because its electronegativity, it's what, for example, has been done in 2005. It's a patent that has been filed by Pascal Chabert at École Polytechnique here in 2005. And the idea was using iodine for electronegative propulsion, because iodine is able to make negative ions. So you want to use negative and positive ions to successively accelerate your propellant for your thrust. Now, the most recent applications are using iodine despite its electronegativity. You want it to make no negative ions, and you want it to behave as if it was xenon. And it's working. The team in the US is using it in big graded ion thrusters, and they show that the performances are similar or even sometimes better than xenon. A team in Germany is using it in small graded ion thrusters. So this one was Hall effect thruster, big Hall effect thrusters. This one is small graded ion thrusters, and they show that for some parameter in mass flow and beam current, iodine is as good in green or even better in red at sustaining a plasma. And in France, we have the Thrust.me company that is commercializing thruster working on iodine, and they are selling similar performances as their version for xenon. It's important to know the physics of the plasma when we want to do a thruster. For example, in iodine, you have molecules on atom, and depending on how much your plasma is dissociated, that will change the average mass, M, in your plasma, and the average mass will impact your ISP, your neutral losses, and if you have a lower ISP, you could have a higher ion mass flow, so hence a possibility of a higher thrust. At the same time, people have often neglected or less studied surface reactions, but now that the thrusters are getting smaller, we are looking at a surface to volume ratio that is higher. So we need to know more about the surface reaction to know what's happening in the plasma. Then there is more recent discussion, for example, about the plume diversion that is shown to be smaller in iodine, and this could be linked to the presence of negative ion. So all this question needs to be studied from a physics point of view before it becomes an engineer matter. But the iodine plasmas are not well studied, at least not in open literature that we can find in laboratories. No available data and diagnostics are scarce. Just two examples. The coefficients from the most famous, most used global model for iodine have not been recalculated, some of them since the 1960s. And if you go on Google Scholar and you type iodine plasma, you will get a bit more than 500 results. You may think it's good, but if you go to more classical plasma, so xenon, chlorine, or oxygen, you go into the thousands or hundreds of thousands of results because they have much more applications. So we will study these iodine plasmas. And if I need to find a line for my presentation of today, I can remind you that people are using iodine now despite its electronegativity, hoping that it will act as much as possible like a xenon plasma. So the question I choose to ask is, to what extent can we really neglect the molecular and electronegative features of iodine plasmas? To answer these questions, I have two tools at my disposal: the theory and the numerical models, in my case in one single block, and the experimental data. I will present them both, and I will show to you how they disagree, because they will disagree. And from this disagreement, we can start looking, and I will present some leads to try to understand those disagreements and to see how they can help us improve our understanding of iodine plasmas. To be completely clear, my experimental data part will be separated in two. First, I will present optical diagnostics, emission spectroscopy, and laser absorption, broadband absorption as well, and then electrical diagnostics with an example of long-mirror probes to measure the electron population. So this is my outline for the rest of the talk. Let's start with the theory of numerical model. I'll give you an overview of what I mean by using theory of numerical models. You use the numerical models to characterize the plasma. And what I mean here by characterizing the plasma is knowing the density and the temperature of each species in the plasma. My model is a global model. That means that all those species will be averaged over the volume. So I have 6 species that I consider in my plasma. All the rest are neglected because they are shown not to be very important. And all those species are connected together. The molecules can dissociate, whether they are I2 or I2+. They can dissociate just by giving neutrals or by creating new ions, by dissociative ionization or by dissociative attachment. They can ionize, so I and I2 will give the corresponding ions. Then you have detachment, your I- will give you back an electron. You have wall recombination, that's surface reactions. That's what happens when the I atoms will go back as an I2 molecule. That's a really important reaction that we don't know well. And then you have a lot of charge exchanges when ions and atoms will exchange their charges. And this entire chemistry is the reason why chemistry of iodine plasmas is eminently more complex than noble gas plasmas. You have very good people that are working on xenon plasmas, but they are mostly working with the atom, the corresponding ion, and electrons. So the chemistry is much easier. If you want to put this into a model, you characterize each reaction, and each reaction here is characterized only by a rate and a threshold energy. For example, if you have a reaction like the ionization, and the I atom will give you I plus ion, you will have an equation that tells you that the variation of the density of the products is proportional to the variation of the density of the reactants, sorry. And then you can say that the power that is lost by the electron population, which is the main energy carrier, is again the same coefficients times an electron energy. So if you know those two values, you know everything about your reactions, and you can run your model. Those parameters, they all come from what we call cross sections. It's in square meters, and it's somehow the probability of a reaction to happen during a collision with an electron at a certain energy. It looks like this for 3 reactions. Example: high excitation, high ionization, elastic collisions. And you need people to calculate that. And not always they want to calculate that, and when they do, it's really hard to find other people to make a comparison. So the threshold energy are the first non-zero value here, and to get the reaction rates, you need to integrate this over the distribution of your electrons. So you know the temperature of the electrons, then you can assume a distribution in energy. If they have a temperature, that doesn't mean they have all the same energy, you have a distribution. You have 2 classical distributions here, and when I'm using the Maxwellian for this talk. And when you integrate, you get a reaction rates as a function of electron temperature that will tell you, depending on the temperature of the electron, how the reaction rate is changing. You are adding this contribution for all equations. So you have an equation like this for all densities, you have an equation like this for the power. You need to add, and it's very important, the surface reactions. So you have a lot of physics involved in, for example, how much energy the electrons are bringing to the walls. I'm not talking about that now. And you get yourself with a system of 7 equations, a variation of density for each species, and a variation of the power of the electrons. You will solve those equations, and that will give you, at the steady state, the value of densities and the value of power. If you have the value of densities, you can as well have the value of some mixed parameter, for example, the dissociation, which is a ratio of I over I plus I2, and it's shown in the model that it's very high, so the plasma in the model is quasi-completely dissociated, at least if you have some power in it, or the electronegativity, which is the amount of negative ions divided by the amount of electrons. And it's seen that in my plasma, you don't really have negative ions because the maximum value here is 2. And if you have negative ions, usually those values will get up to 1,000, 10,000, 100,000. So my model will tell me that there is a lot of dissociation and no electronegativity. If I recap, my model is able to give me the density of each species averaged over the volume, the temperature of the electron, and to run, I need to give it the temperature of all those species. I consider all the species at the same temperature, and I use it as an input. In my thesis, and I won't go into details here, I just lost the screen in the amphithéâtre, sorry for people in the chat. Wait for the live, okay, it's back. I studied the sensitivity to the EDF, for example. I added some uncertainty quantification in the model. Those are screenshots of the manuscript that you will see again in no time. Sorry for this again. I lost the screen in the RPD. It's not super stable. Sorry for that. I worked on adding some electronegative values in the plasma, for example, the electronegative wall fluxes. I rewrote the entire code in Python using a modular approach with the idea of sharing it and open sourcing it online for more people to use it, with a layer of code standardization so that it can be used for different clusters and different gas without changing the structure of the code. But I won't go into this, and instead I will go to experimental data. And if you want experimental data, the first thing you need to have first is an iodine plasmas. And that's somehow the first result of my thesis. If yes, you can get an iodine plasma running daily in a setup in the lab. You just need to take care of the people and of the machine. The people first, because iodine, even if it's way easier to work with it, like for example chlorine, you still need to have some gloves, you still need to work under a fume hood, wear a mask, people are used to it now, and so that you don't damage your health with that. For the machines as well, because for example, in the extreme case, these are the results of an unscheduled corrosion test that we perform at the lab. If you let the iodine deposit in your pipes, and then you let the pipes in open air for a couple of weeks, you will get some deterioration that is usually something you don't want to happen in your plasma. This is the main setup I'm using. I'll spend the next some slides explaining what you see. The big bubble here, it's called bubble, is a vacuum chamber. It's a chamber in which you make vacuum because your plasma needs vacuum to run. It's connected to a corrosion-adapted turbo pump and a standard scroll pump. Then you connect on it the ionization chamber from Pégase. That's where we make our plasma. For those of you that know Pégase, I removed the acceleration stage and the ionization and the magnetic barrier. And then you put your iodine crystals that you connect through a mass flow controller that will control the flow of iodine. If you do this, nothing happens because, as we said, iodine is solid and you need to heat it to get some pressure. For example, if you need to have 001 bar, which is what we want, you need to go around 75 degrees. So we heat the entire injection line, and it's very important that you keep it heated all the time, even if the plasma is off, to avoid deposition. Similarly, we have a nitrogen trap at the back when we cool at minus 200 degrees, and that will allow us to catch the iodine after it's been used in the plasma chamber. Then we have some power. We have a 4 megahertz RF generator that can give you 200, 300 watts. That we connect to an ICP antenna. That's a flat coil in which we run a current, and we have a plasma that is created by induction. That's an inductively coupled plasma. We calibrate the power used by a famous method by Valérie Kodiak. And still there, nothing happens, because if you just put iodine and power, it's very hard to turn on, so we need to make first a mixture with another gas, usually argon. We could use xenon if you have money to spend. So we use argon, and then you can make a mix of plasma, turn on the power, and you get an iodine plasma to make your experiment. That was my setup. Now that we have this setup, we can look into the first diagnostics, and it's optical diagnostics, and more particularly emission spectroscopy that will give us some qualitative measurements. Emission spectroscopy is what happens when you put an optical fiber and a spectrometer in front of a plasma, and you look at the repartition of the light that is going out. Here, what you see, if I overlap the visible spectrum, is a lot of UV emission, a lot of infrared emission on some bands. And thanks to the available data sets, you can reconnect what you see. For example, the peaks in the infrared here are from iodine atoms. That's when electrons move into the energies of the atoms. So when an electron will go down the energy ladder, it will emit a light at the given frequency. And here, it's iodine, it's molecular emission bands that I will talk about more later. This is very important to allow us to go into the next diagnostic, which is laser absorption spectroscopy that we use to measure the density and temperature of ion atoms. We go back to this. If you have an emission line, that means that there is an electron going down the energy ladder. Physics tells you that it can go up again if you send the light at the very same energy. So what you expect, if you send light on your very wavelength, you will see an absorption dip. That's what we see. It's more complex than just one absorption line because you have a hyperfine structure. But we can see 60% of absorption, which is huge. A very good signal-to-noise ratio, and from the Doppler broadening here, we can get the temperature of the plasma. But we couldn't get the plasma density because first it's in the excited states and we don't have any collisional relative model to tell us how the states are sorted here. And then the transition is not calibrated. We don't have theoretical data to study. So we need to go both in the fundamental and somewhere in the fundamental state when it's calibrated. We have only one candidate and luckily it's been calibrated. So we will use this one. The problem if it's a magnetic dipolar transition, and the magnetic dipolar transitions have absorption that are 10,000 times smaller than the electric dipolar transitions. So the final results I will obtain is our spectrum like this, and we are showing 1.5% absorption, and this took lots of weeks to get. I will explain you more how I get this kind of data. The first thing you want, if you want to have a good signal-to-noise ratio, is to increase the time that the light is passing in the plasma. So we install the setup, we have the laser here, that is going 9 times into the plasma and then out in the photodiode. If you look at the spectrometer, that's what you get. You see a long time, the diode will vary the wavelengths, and you will see some absorption here. That's the 6 peaks I showed earlier. That's good, but you don't know what the wavelength is, and you need that. So you need to calibrate those data. We do it with the Fabry-Perot interferometer. And now you know at which wave number you are. and then you need to correct for the slope, and this is done with a normalization photodiode, and we get our transmission here, and you see again the 1% absorption. So keep in mind that we are at 1.3 microns, and when you do all this alignment, you don't see ionization. Once you have this transmission, you can find the density by integrating the peaks and the temperature by looking at the Doppler width. We did this, I did that for different pressure and different power to see how it's moving, how it's changing in the plasma. And what we saw, first, it's all our data points are here, so the change of color is when I increase the pressure, is that the density and the temperature are both stable with the discharge power. That means that we are at a regime when if you add more power, you will not dissociate more molecules. You are at a stable regime. If I compare to what's expected in the code, it's working well because the model is also assuming that you will get something rather stable. The error bars that you see here are due to the fact that the cross-section is now at plus or minus 24%, so that you have a big error bar. So we are still a bit too high in the model. I will tell you more now. Because when we change pressure, you saw that you are linear with pressure. That's interesting. And this linearity is somehow predicted, but we are around twice too low. So we are measuring a density that is lower than predicted by the model. So the high density is lower than predicted by the model. This data will be used in the rest of the presentation. For the temperature, we have a function now that we will use as an input of the model. And for the density and temperature of I atoms, we will use it to know more about the dissociation degree. If we want to measure the dissociation degree, either we can use the pressure as a reference, or we can measure directly the density of I2 and then compare the ratio. That's what we do next. Now we measure the line integrated values of I and I temperature, but now we will go to a last diagnostic called broadband spectroscopy, last optical diagnostics, to measure the I2 density. It's the same idea. We look at the emission. We know that if there is emission, that's electrons going down the energy ladder. We look where is the path when you can go up the same energy ladder. That gives you absorption peaks. That's theoretical data. We have two absorption peaks, one in the vacuum ultraviolet. We can't prove that in the lab here because it's absorbed by ambient air. And an absorption in the visible that looks easier, and it's good because it's in the fundamental. That means it's good for us to use. The absorption is in the green and yellow, so we need to do that. We need a lamp that is emitting in the green and yellow. We found one, it's an halogen lamp that we have at the lab. We have an emission in the green and yellow here, that's what we will use. We also have a lot of red that is not needed for now. We make two passes in the plasmas, one in the plasma, 1 and 2, and we get the light in the spectrometer, and we compare the light before and the light after, the light without plasma and the light with plasma. What we see, when we test with gas, for now just gas, we don't turn any power on, you see that you have less light in the region when you expected absorption, so it's good. If you compute the corresponding optical depth by taking the logarithm of the ratio of those curves, you see an absorption here, that's good. If you increase the pressure, absorption increasing, that's good, for now everything is fine. Normally what you would do now is divide this by the density, by the absorption length, our two paths, 40 centimeters total, and the cross section. And you should get something that is constant with wavelengths, otherwise that means your method is not good. It's not constant with wavelength. That was a surprise, but we can easily explain that. First, on both sides, we have the region where either we don't have enough light for the lamp, so the signal to noise ratio is really bad, or we don't have any absorption, so the signal to noise ratio is really bad. Now we look into this. This we can explain, because when we look at the shape we measure, and we compare to the shape we expect, we can see that there is a big change of behavior at 500 nanometers. Before that, everything's fine. After that, it's not working, because the shape that was measured experimentally was done by the community that is studying atmosphere. So they are using those cross-sections to quantify how much iodine there is above oceans, for example, depending on the weather. So they did that with external pressure that was not vacuum like I did. And this transition here are from bound state to bound state, and this is very sensitive to the pressure. That means that what we see is really not what they see, and that's normal. But the left part, it's a transition from bound state to free state, and that does not depend on pressure. So what it tells us that if we can use them, but only until 500 nanometers. So that's what we will do. We will focus ourselves on the region for 480 to 500 nanometers. And when you calibrate by changing the pressure, you measure the I2 density, and we find, well, again, the ideal gas law we expected. So it's the first reason why the method is validated. We are even more convinced because the shape we measure, even when the plasma is on, is the same as expected until 500 nanometers, so it gives us confidence. We measure I when the plasma is on, and when the plasma is on, it's much more complex from an experimental point of view because you have the plasma emission that's added, so you don't see the absorption anymore. So you need to really make good data analysis by removing the plasma emission every time that the plasma emission is changing depending on our plasma parameters. And we get again I2 density as a function of discharge power, as a function of pressure. When we compare this to the model, we find that it's really not working. So it was somehow working for I, it's not working anymore for I2. There's one reason for that, there's one effect we can already subtract. It's due to the setup we chose to work with. To be able to have light going through a plasma, you need optical access, so you need windows, but you need to have still your plasma in vacuum, so you need windows that are keeping the vacuum on one side. And we used windows at the Brewster angle. It's an angle that will cancel the reflection from this polarized light. That was very useful for the I atoms experiments. And, but it's not only for this, because if you put windows too close from your plasma, your iodine will deteriorate them and you cannot measure anything. And in this window, you don't have any plasma. You have some gas, but you don't have plasma. So we need to understand how much gas there is in it to subtract it from our data and get the value in the middle. For now, what we did without knowing it was considering everything constant. So this is the I2 density increasing to the right. The first model we could do as plasma physicists is say, okay, quadratic curve. It makes sense because you have a neutral depletion at the middle because the gas is warmer, you have electrons pushing the neutrals on the side, you have the dissociation here. Where on the walls you have more recombination, it's colder, and this point you can calibrate by knowing the pressure you measure. But this is too smooth for our situation. So another model could be saying that the windows are full of isobar iodine molecules alone, and then everything else is in the middle, and we can consider it constant because it's super low anyway. We know that the truth is somewhere in the middle, so I'm taking a model which is exactly in the middle, the average of both these models. The area is constrained by the absorption we measure, and the value at the side are constrained by the pressure we measure in the system, so it's an external pressure measurement. It may not be super physical, completely physical, but what we are looking is the value at the middle, and it's a good approximation. When you do this correction, you see that everything is much lower. That's what we expect, because we subtracted the values that were in the windows. It's so much lower that for some values, it brings negative values, and for the sake of the demonstration here, we subtract those. And you see now that you are bringing a completely different order of magnitude, but also a completely different trend, because now it's decreased, the I2 density is decreasing with discharge power, and quite constant with pressure. You don't see any difference in the pressure here. And if you compare to the model now, we are much closer to the model. It's still too high. We still have an I2 density that is larger than predicted by the model. I2 density lower than the model, I density lower than the model, I2 density larger than the model. So these experiments, broadband spectroscopy, gave us the length, the line integrated value of I2 density. The last experimental that I present is a Lonely probe experiment. So we put a Lonely probe in the plasma that looks like this. We have two pins here that are measuring currents depending on the voltage you put in the probe, and that gives you information about your electrons. It's in the middle of the plasma, not exactly, a bit on the side, and you can see the mechanical arm that is used to bring it in the plasma here. We removed the grid for the picture. We use the Valery-Godiac probe system to give us the IV curves and the electron energy distribution functions. And what we get from that is the electron density and the electron temperature. The electron density is first increasing with pressure because you get more collisions, including ionization collisions, and that makes you more electron density. When the pressure increases too much, these collisions are not so effective anymore, so the electron density decreases, and the temperature decreases with pressure. It stabilizes around 2 electron volts, which is quite normal if you are used to molecular plasma. If we compare to the model, it's somehow working well for the temperature. We have a problem more than to fitting the density, the pressure, but the temperature are good. But the density with pressure is around 3 times lower. We are measuring 3 times lower electron density. But that's not the only problem. If I scale this, if I divide by 3, I can see that the decrease I'm expecting is way higher. So we are decreasing way faster than we want. That's something we investigated with Benjamin in the room. And we show that if you move the probe in the plasma, you see that we are not homogeneous as the model would expect. We are not in an homogeneous plasma. We see gradients. The gradients are quite low if you are at this kind of pressure, that's the points here. But when you go here, so that's 4.5 Pascal, way higher than the scale here, you see huge gradients, and the probe is localized here. So what I mean is now, the value we measure, we know that it's lower, that's the middle value, the center value, or even the average. And we know this discrepancy is higher when the pressure is moving. So we don't have the rest of the curve here, sorry, because of the COVID, basically. But you can know that what we measure is lower than what we should measure in the average. So that's part of the explanation. So the Langley probe experiment did measure the electron density, the electron temperature, and it has been shown in 2017 in the same setup by Pascal and Romain that if you really go in details by analyzing those data, you can get a value of the electronegativity, so the ratio of I- atoms, and she showed that the negative ions were completely negligible. That was the theory and the numerical models and the experimental data, and I will quickly recap you all the disagree. Before I do so, I must remind you that we have predictions on measurements that are not exactly at the same position. The predictions of average on the volume, and what we measure is along either averaged along the line of sight of the plasma or taken at a single point. That makes the comparison quite tricky sometimes, hence the need for models and so on. But once we know this, we can say that we have electron measurements in good agreement in the models, except that we are 3 times higher for the electron density, but we can explain part of this discrepancy by the plasma localization. Plasma is moving away to the antenna. We measure successfully the eye absorption with a laser. That was the first time it was done, and we measure something that is lower than expected. We also measure for the first time by broadband absorption spectroscopy the I2 density, and it's too low compared to it's too high compared to what we expected. And if you put that together, we get a value of the dissociation degree, either that we divide the eye density by the total density, or we divide the partial pressure by the total pressure we measured, and we see that when we expected something from 100% or 95%, we measure something that is in the center, closer than 60 to 80% when we look at those experiments. So we show that in the center we are only 60 to 80% dissociated. That's the discrepancy. From this, what can we say? So now I will give you some of my opinions about what this data can tell us about the understanding of iodine plasmas. I'm not saying that either the model is wrong or that the experiments are wrong, but I will use the fact that I have a model that I coded in-house to change the parameters and see if by changing those parameters I can reconciliate my experiments and the model. We saw that we have too many I2 in the experiment. That means not enough in the model. So the first thing we can do is go into the equation that is measuring I2 and see what we can change. We see that I2 is mostly created because you inject I2, so you have I2 because you put it manually back, but also because the I atoms are recombining at the walls, and this is much more important than the I2 injections. And we see that they are mostly lost by dissociation. Everything else is rather negligible at the first time. I will emphasize this wall recombination now, but the others are quite similar. And I'm emphasizing this one because it's something that is not well known. So it was part of the objective of the PhD is to be able to characterize the recombination rate at the walls. The recombination happens when a lonely I atom go into a wall and find another lonely I atom and get back as a molecule. You have a probability for that, that's gamma. And in Cl2 plasma, depending on the parameters for the plasma, for the walls, for the temperature, they show that it could go from 2 to 80%. In my model, I took 10. And I see that I don't have enough recombination. So it could be an easy thought to say, okay, if I increase those gamma, doesn't seem too bad, and then it would improve my measurements. Actually, it somehow does. So we see that if we increase gamma, we are lowering this curve and it's getting closer to my actual data. But I can't claim that it's improving the predictions because here we measured something that was very linear. And the trend corresponds way better to a trend with a very low gamma because you are getting away from linearity if you increase your recombination. So we are not really getting closer. You can see it as well if the variation with discharge power. And something that is not good either is that it's not changing anything in your electron measurements. So you are not improving anything in the electrons because they don't depend on the wall recombination factor. So this parameter, we really hoped it could help, but it's not really fixing dissociation nor electron energy. And my work is rather suggesting that for iodine in my setup, we have a value that is around or below 10%. The problem we have on electrons, that we are measuring less electrons than we expect, suggests that we are losing power somewhere in our physical system, because this power would create more electrons. So we can go in the power equation in the second step. If you go in the power equation, you have power losses, and to see what's happening, I will increase artificially those power losses and see if by adding some power loss, I can get something better. And we could see that, as expected, it's decreasing our expectations of electrons. So if you remove some power, you will remove some of electrons. So that's good, that's what we want. And surprisingly, or not, depending on the people, but for me it was surprising, it also helps a lot reconciliating the dissociation model, because you have less electrons, so you will have less dissociation reactions because they need an electron impact for this. So it works as well for the with pressure. So adding more power losses to the model is the only lead I have now to fix both the electron density and the dissociation in my model. So it's something that is very, very likely. And in addition to that, it is something we can expect because in the model, all molecular effect of molecular losses are neglected because we saw that the models expect that there is no molecules anymore. And we have shown some molecules, so they can be molecular related losses. That was the outline. That was my talk. And now I can say a couple of things to conclude it properly. The first one is to answer my questions. At first, to what extent can we neglect the molecular and electronegative features of iodine plasmas? I have two conclusions for that from my work. The first one is that the plasma is still partly molecular. We know this because, well, I measured it. So it was measured that we have around 20 to 40% of molecules at the center. And as I said, it's a likely source of power losses. We need some more power loss in our model. And if you add those molecules, it makes a natural source of power losses. So it's something that gets well together. And second, the electronegative negligible. It was shown by Pascal and Romain in the previous thesis by long probe measurements. But as well, if you look at the magnitude of the electron density, if you have high electronegative plasma, you would usually get lower electron density. So it goes in the right direction, but this was actual measurements. The second conclusion I can do is talking more about perspective. If I had 3 more years of PhD right now, which I would be happy to, I would do first more measurements. More measurements would be, for example, to get absorption experiments at lower pressure. If you have lower pressure, you will still have way lower signal-to-noise ratio, so you need to make way more passes in your plasma. And that can be done with a method called cavity ring down spectroscopy, where you can make 100,000 passes. We tried, it was not successful, but new PhD students could try again. And we would like some measurements of the negative ion or positive ion temperature to constrain, for example, the electronegativity measurements from long probe. I wish I had spatially and temporally resolved measurements, so being able to know where exactly, what I have exactly at a certain point, so we can do this with laser-induced fluorescence or 2-photon laser-induced fluorescence. We have some schemes that have been proposed in the literature, but also using the long probe I have to probe all the places in the plasma. Then I wish I had spatially resolved models. That's some work ongoing, for example, by Benjamin, and some work has been done by Roman as well. Having 1D, 2D, 3D models, whether it's peak, fluid cause, or anything, to know more about what's happening in the, what we can expect in the plasma. And last, we really need stronger theoretical data about iodine. That is cross-sections, so the cross-section of reactions, because the one we use in the model are not well validated by the community, but as well cross-section of absorption of the photon absorption in the fundamental state, in excited states. I will need collisional radiative model to know how the states of the electrons are reparted are sorted in the energy levels. We need the oscillator strengths to be able to analyze some absorption data. More measurements, spatially and temporally resolved measurements, spatially resolved model, and stronger theoretical data about iodine. That would be my wish list. That was my presentation. Thank you very much, and I'm ready to move to the question part of the defense. Thank you.
So, thank you very much. I will first ask your rapporteur to ask a question. It is tradition So the first person normally, well, okay, now they're all far away, but the one that is further, so it's Dr. Gans, Professor Gans. So please, can you ask the question?
Yes, okay, thank you very much. Can you hear me fine as well?
Yes.
Okay, good. So, yeah, first of all, I would also like to thank you for the nice presentation, also congratulate you overall for the very nice work. I really very much enjoyed it, in particular the combination between the modeling and the advanced diagnostics, which, in my personal view, is the best way to understand plasmas in general. And it is also good to see that you have actually got a lot of nice results and understanding out of it. So, hence, actually, my questions are actually focused on the understanding, which is kind of the last chapter and the last part of your talk as well, where you discuss the variety of different options, why there may still be disagreements between the model and your experimental results. So, if I understand correctly, so what you see in the experiment is that your electron densities in the experiment are actually lower than predicted by the model. At the same time, your degree of dissociation in the experiment is also lower than predicted by your model. So if this is the case, as you have actually kind of discussed in your, those slides, in your discussion of the power, so essentially you have too many electrons in your model, and that also results in too many atoms, essentially, or let's say a depletion of your molecules, too much depletion of your molecules in the model. So essentially, what you need to find is to find a mechanism where you lose electrons. And once you lose the electrons, you also lose your dissociation with them because it's the electrons which do the dissociation. Would you agree with that statement, first of all?
Yes.
Okay, good. Now, one mechanism to lose electrons is to actually make negative ions.
Yes.
I was a bit surprised that you didn't discuss that as a possibility. So maybe you're a negative ion. Maybe you just lose more electrons to negative ions than predicted. Do you think that's a likely scenario?
That's something we thought indeed as a likely scenario for the very reason that the fact that we had less electrons on more atoms make that the plasma is looking more to a chlorine plasma, for example. That was the question we had when we started experiments, was basically to sort our plasma to see whether it was looking more like a xenon plasma or looking more than a chlorine plasma when you have a lot of molecules. And because molecules are the only way to create negative ions. So indeed, if you have molecules, you should have negative ions. We discussed this, and that's the reason when we performed the analysis with the long mirror probe. So I used the method from Jérôme Brenin in 2014 that was used as well by Packan, and we showed that the electronegativity in my case was negligible. I could not get actual values, but Packan did, and he showed that the electronegativity stayed below 0.05 all the time. I can find where it is in the manuscript actually. It's in the electrical diagnostics part. Yes, so page 200 and before. We show that the electronegativity I could measure. I'm not putting this. I did not put the results because what I could measure, I will show it on slide in the room as well. Sorry for that. So that the jury here can follow. like the electronegativity, so that the figure 413 of the manuscript, that the electronegativity I could measure with my method, and I didn't like it because the value I could find was moving between minus 0.1 basically to 0.7, depending on the fit parameters I was using. So I prefer not discuss the results and take the one from Pascaline that were much nicer, but what we can see anyway is that it's very unlikely that we are above 1 as an electronegativity. So the negative ions is really lower. So we expected some negative ions here, and we showed that it's not the case.
Okay, because if you look at the left-hand plot on the slide you have on the screen,
yes,
where you vary the gas pressure, it is also the case that the trend doesn't really fit that well. So because the stronger decrease towards higher pressure is not really helpful for but at the same time, the negative ion density goes up with pressure as well. Is that right?
Yes, that's expected from the model actually.
Yeah, so if there would be an effect of negative ions, that would also fix kind of the pressure trend in the electron density. Do you agree with that?
It would participate too, but what I'm really interested would be, and that's something we are sad we couldn't do because of the fact that we couldn't access the lab due to COVID, but I did show that part of this stronger decrease was due to the plasma localization. So what I really hope to be able to do is to take into account this plasma localization and see what I have left as a stronger decrease. So if I have a stronger decrease as well, I would agree that this is that ion negativity, that negative ions is a likely cause. But for now, we have the feeling, as you can see the magnitude of the gradients, that the main effect should be the plasma localization.
Okay, fair enough. Then I have another question going kind of in a similar direction, but it's not in a headlines anymore now. So, so one of your light year explanation is kind of the power approach that you say, like, in principle, if you fix your power, then you're kind of fixing your problems, right? So you're saying, like, if you use a lower power in the model, then things fit better because you get less electrons and then you get less dissociation. Everything's good, right?
Yes.
So now I have a question about the gas temperature in that context. So in your model, you just set the gas temperature. You don't self-consistently calculate it. You just take the experimentally measured gas temperature. Is that correct?
Indeed, yes.
So if you set the gas temperature in your model of whatever, 1000 Kelvin or so, whatever you use,
That's the order, yes.
rather than 300, I mean, where does this gas temperature come from? I mean, is that not equivalent to putting extra power into your model?
I see what you mean. I would have first seen it the other way, because if you are the fact that I would have said that the fact that we are eating the gas would be one power loss factor. That the power in the model that is going in the electrons is actually in our setup going to hit the gas. I don't know. I'm not sure it's what you mentioned, but in my way, now that you mentioned that, I could see that the fact that the gas is heating could be one way that we are losing power in our system. That would not explain the discrepancy with the model, because we are using those values as a model input.
So essentially what I'm saying is, in reality, you actually lose power to heat the gas.
Yes.
Now, that power is essentially lost for the plasma because it just goes into the heating point.
Yes.
Now, if you, in your model, put the heating into the model separately to the power, that is in a way equivalent to giving the model some extra power for free.
Yes, I see what you mean. Two-part answer. So the first one, yes. The second part is we did try that. So I have actually a section in my chapter 2 when I studied the effect of varying the gas temperature, and I did show that varying the gas temperature has two effects, and none of them is to really change the electron density, because in the equation the gas temperature is never really coming in important factors, but it has a big effect in changing the gas pressure, because the way I'm calculating the gas pressure in the model is to say that everything is an ideal gas, and I have the density, and then I measure I have the temperature, and then I get the pressure. And that's very important. That's why it was very important to get the temperature, because we could get the same results at the pressure multiplied by 2, depending what the gas temperature we took. But we did show that the model was not able. So either it's wrong, or just the model is not able to capture it. But we don't see the phenomenon you mentioned in the model when I changed the gas temperature.
Okay. Okay, fair enough. Is there a related question to gas temperature? It's like, so do you have a feeling, maybe from even other people's work, what do you think is the main gas heating mechanism in your plasma?
I did know that. So to be fair, the gas heating processes was included in the model when I got it, because it was done from Pascal Chabert. If you look in the paper from Pascal from 2012, or the paper from Pascal in 2016, and the way I did was to first run the model with the gas heating, see that the temperature I was gaining was coherent with what I was measuring, so the model was capable of outputting temperature of 1000 Kelvin. And then I say, okay, the temperature is likely, but now if I want to capture it, to capture the real dynamics in my model, so the variation with pressure, I need to input the temperature myself. Once I've said that, I did not answer your question. And we have a heating mechanism by collision with electrons, and I do not believe that's the main parameter. We have a cooling mechanism because of the walls and the relay section length of the temperature.
What about the dissociation? Would you expect energy to come out of the dissociation process?
Yes, it's something they see in chlorine, and it's so yes, because you have because the atoms are going out with excess energy, with some excess energy of the electrons. So the energy balance makes that the resulting atoms have more temperatures. So yes, that might be the. So if you tell me that's the largest effect, I would trust you, but I can definitely understand that's some process. I know we can quite easily look at that, because I have so I don't have it in my. Do I have it in my backup slides? I don't have it in my backup slides, but I have the. So we have an equation for the power of the electrons, and we have basically the same for the power of for the gas temperature, and we can really solve the different equations. So we could do the same work that I did for the dissociation, for example, or from the wall combination, by changing the parameters such that the temperature relaxation length or the energy that is taken in the dissociation, and see if we could capture those behavior as well. So that could be a way to I don't believe that's something including in Pascal's work. That would add a loss channel, as you mentioned before, and that would increase the temperature of the ions.
Yeah.
I agree.
Okay, so you think that may be something for the future to look into?
Yes.
Okay. Another question on the gas temperature. Do you think charge exchange collisions could play a role? Because, in particular, in the sheath region, the ion is actually bigger energy.
Yes.
And if they undergo charge exchange, they give that energy to the neutrals.
Yes, and that's the same for negative ions. So negative ions tend to be warmer because they cannot cool at the walls because they are trapped by the sheaths, and they would bring some more heating by charge exchanges as well. Yes, that's definitely possible. I showed in my in the dedicated analysis I did when I tried to look in the model how the particle was disappearing, for example, page 87 and so on, that the charge exchanges were really not a big effect in the way the particles are created or lost, but that does not mean it's not a big effect in the way that the temperature is changing. So that's something worth looking into.
Okay. Right. Okay, that's enough for asking about the gas temperature. So one final question is, again, it goes in the direction of what is not included. It's a short one. So what do you think? I mean, one of the potential things of power you mentioned is vibrational excitation, for example. Because we still have molecules.
Yes.
Could you maybe comment a bit more on what vibrational excitation could do to your plasma if you included that?
Yes. Well, any excitations could be added. We are not taking into electronic excitation, but we are not taking any excitation in consideration for the molecules. One thing I can think of, because I happen to work with in the same lab that the vibrational excitation usually increases the dissociation, and that's something that we can really see, for example, in the work from Gudmundsson in chloride, that they do have the data of cross-section of dissociation depending on the vibrational level, and they say that you can dissociate 10 times more if you are at V equal 4 than if you are at V equal 1. That was part of the theoretical data that I'm hoping to have one day, that I mentioned in the conclusions. So if you add this, you would increase the dissociation.
What about the negative ions?
What about the negative ions?
Could the vibrational excitation also influence the negative ions?
Well, I don't know, but the reason how it could is because the vibrational excitation would increase dissociative attachment reactions, but I'm not sure if that's something that is likely to happen. But other than that, I don't see how it could influence the negative ions.
Yeah, so usually vibrational excitation also helps the formation of negative ions, so you would increase your electronegativity.
Okay.
If you include that. I would think.
Okay, so through dissociative attachment or through an additional mechanism? Okay.
Yeah.
Thank you.
Okay, I think these are all the comments I have. So thanks for clarifying some of them.
Any further questions?
Thank you very much.
So thank you for your questions and this nice discussion. So the next referee is Dr. Garrigues.
Okay. Hello. Do you hear me? Yes.
Yes.
Okay.
Perfectly.
So thank you, Katarina. And so I want just to congratulate you about your work, what you have done. I think it's a very. I put in my report. I talk about the pioneer work. I think it's very important for the EP community that finally your work shows that we can work with iodine, and it's possible to use iodine as a propellant gas. That's very important. And the complete, through your numerical model and experimental work, and technical diagnostic, you finally show a kind of complete or very important image, I think, of plasma properties with iodine, and that's, I think, is almost unique as far as I know. So now I put my comments and questions. First question concerns the cross-section. If I understand well, you use calculated cross-section, right?
Indeed.
Yes. Have you tried to do some comparisons, what we can find, and if we can find with cross-sections that are measured and in the literature? some data about that?
My quick answer is no, but let me think again about it. No, not from the reactions. We have so cross section is also something I have for absorption. So in that case, it's different. But for the reactions, the cross section I mentioned from the model, no, it's only so we have so it's calculation that was written at the lab by the team from Hamilton and the team from Quantemol just before I arrived. And I don't believe we had other source before. Actually, that was the main reason why they asked Quantemol about those cross sections.
Yeah, no, because I think it could be maybe an origin of some also discrepancy between calculation and measurements.
I do hope that we have experimentalist physicists that are listening to this and will take some actions to measure those cross sections.
Yeah, it's important. But I mean, I think the main challenge, for example, is very important just to be or maybe calculate eventually some data if necessary. I was also interested by finally what you have done, with your Monte Carlo simulation that calculate the error bar. Can you comment about that, please, a bit?
Yes.
Okay, you have prepared some slides on that.
No, not directly. But I have not on this question. But I can show what you are talking. I can show a bit more about what we are talking about. Here we are.
Yeah, it was the slide
Okay, so
44.
Yes, so I'm showing I'm showing on screen the equivalent part of the manuscript that you have. I'm showing the figure 221 on the next pages. So yes, so the question was to talk about it generally for now. That's it.
Yeah, generally, and I have two questions.
So the idea, as you mentioned, is that we have a very low data about the cross sections and about the temperature, or even about the electron energy distribution function. And the first idea I had when I come was when we measure when we compare experiments and models, we always include the error bars of the experiments, but we never include the error bars of the models. And we can see that we have quite some large error bars on the experiments, and I wanted to see what they look like in the models as well. So we had worked on this with the team from INRIA for a couple of months, and on one of the so we did two actions about this. The first one was just to make error bars, as you said, as I show on figure 221. So I have I do this by instead of taking one reaction rate, I'm taking a distribution for each reaction rate. So I'm taking a log normal distribution, which is which is normal distribution in log space. That has a good way of never going to zero. And we estimate an uncertainty, and that was the tricky part because so when I arrived, I was quite naive and said, well, just cross section just got calculated, so I can assume a 5% error bar, something like this. And apparently, that's not something you can do. So we moved to uncertainties rather large, and when we move this, when we draw every time. Sorry. We draw every time a value, and we do random simulations. So here I have 100,000 simulations, but actually the results are quite converged from 10,000 around, and it gives you an error bar on the results. That was the first thing we did. So we can see on figure 221, for example, that adding, and that's a part of the question of the answer for Timo as well. That's when the biggest error bar on I2 and I minus, and they come from on I2 plus, and they come from the error bar I put on gamma and the wall recombination. Because if you have more recombination, then you have more I2 molecules, and if you have more I2 molecules, you have more I minus ions, and you have more I2 plus ions. So that's the first part. And the second part was to do a sensitivity analysis that I presented as a conference about uncertainty quantification with a lot of people doing math for a living. And the idea is that if you do a dedicated analysis of the uncertainty by moving each parameter at a time, or by having a clever way of moving all parameters together, you can see how much of the uncertainty is coming from what parameters. And what I showed at that time, and I did not put it in the manuscript because it was very preliminary results, is that most of the uncertainty, like putting a 50% or even 100% error bar on the reactions at the cross section, will never have as many effect as putting a 5% error bar on the ionization rate, for example. So we showed that most of the uncertainty from in the volume reactions was coming from what we think as the most well-known reactions, because they are really dominating the plasma chemistry. So the first part. On the second part, we showed that the uncertainty was well sorted between the uncertainty about the chemistry, so about these rates and those energy and the electron energy distribution function, and the uncertainty about the geometry. So I put an uncertainty on the H factors the H2 center density ratios, and that's taking into account that can be an uncertainty about our understanding of physics, but that can also be an uncertainty on the surface state, and so on. And we can see that when you put an uncertainty of 20% or on this H factor, then it carries basically half of your uncertainty of the model. That was two steps. And the next step we did not take, because we moved to optical diagnostics, was to make a mathematical models of all those errors we are behaving, so that you don't have to make 100,000 Monte Carlo simulation every time you want to calculate an error bar.
Okay. And do you think with that method that you can reduce the number of reactions? For example, because you understand that if you want to go towards, like you said, fluid model, of course, you reduce the number of reactions, and it would be very interesting. So have you tried to do that, or to estimate, to have some idea about that?
I did not, for two reasons. The first one, the first one is not a good one. It's more a context than a reason. Is we were more looking into adding some more reaction in the chemistry set than to removing some. And the first answer is that what I see in all the parts, I will show them on screen. So what I saw in all the curves from 225 and before on around is that so you can, for each reaction, look at where the I2 energy, for example, if I take I2, you can look where I2 is gained and where I2 is lost. So for example, on figure 25, you said that if you are looking for I2, you could make a small model with only the dissociation, the ejection, the recombination, and if you keep all the reaction you need to have a good estimate of your electron temperature, which is not a small condition. But if you do the same work on the electron power, so you add more reaction for the electron power, you would find something that is not so far away of your I2 density. But I did not go much further than that, because actually the model you will do will depend of what you want to see. If you ask the question as someone working on thrusters, I get what you will be interested in is the I plus, for example. You will want to know what is the I plus density and what is the electron temperature, because you know that the beam will be depending on the bomb speed and then the density of I plus. And that would make you also a specific data set. But in my case, for example, I was trying to measure the electronegativity. I was not working for a year as a people about thrusters, but as a physicist. And if you look at electronegativity, if you look at dissociation, that's not the same reaction that you take. If you are looking at thruster, you can have the first approximation. That's what we saw. That we see. You cannot take the dissociative attachment because it's third order into the I2 loss processes. that's equivalent to just basically removing I minus ions. But I didn't want to do that because I was actually trying to measure them and to see what we can see. So that's the reason I didn't go much further, because from my perspective, I was in the mood of measuring as much things as I could. I'm not trying to deduce some cluster performances, but the answer is positive. Yes, you can, with what I did, try to select some reactions to input in a fluid model, for example.
Okay, that's nice. Okay. I have a question also about the combination coefficient, but you said in your presentation that finally there is some measurements for chloride. Yeah, I am correct on that.
Yes, that's a review I found in a paper from for Torsteinson and Gudmundsson in 2010 about global model from chloride. They make a review of the recombination ratios that are being measured.
Yeah, and do you remember what was the diagnostic and we can apply maybe for iodine plasma?
I don't remember for this case, but I would be able to give you some methods that would allow us to measure the recombination rate. Yeah. For example, because when they applied it at the lab to measure the recombination rate of oxygen atoms, and that's what I meant by having temporary resolved measurements, because you basically stop your plasma, and the speed at which you will use your atoms is basically depending only on the recombination factors, not a lot of it. So we can definitely do this. We could do it at LPP. We did that for oxygen. The thing is, the setup for iodine are not the same. As Richard Van Gullen said, once you make something an iodine machine, it will stay forever an iodine machine. So that's something we could do, definitely, yes. With other setups, so for example, in Pegas, we are very limiting in optical accesses. So the absorption experiments I did was really what I could, the laser-reduced fluorescence that I wish we can do. If they are done, they will be done in another setup, because we don't have enough optical access to do them here now.
Okay. I have also a question about your power losses. First question, what about the measurement of power losses? Are you confident about the measurement? Because you said that finally you have more, it seems that there is you need somewhere just to have more excitation. For example, just to reduce it in your model, the power, just to increase the power elastic. But what about the experiments? Are you confident about this? You can estimate with good precision?
Yes, if I understand, it's a question I think I expected earlier. If I understand well, you mean like, do I measure properly the power in my setup? Because maybe it's just a problem of reading the power.
It would be a source of difference, I would say.
Yes, that's a question we asked a lot. So as I said, we measure something that were quite constant with power for a long time. And a basic reaction I had in some of my supervisor was to say that probably I was doing I was doing everything wrong with my power supplies, and the power was not really moving at all anyway. So we took a long time recalibrating that. But there is still a big thing we use, and that I have slides for, so I will use them so that it's easier. But you want? Yes, I will show. I'm still showing my screen, so it's fine. Wait, that's the code. That's for. So we are using the Godiac method, and the thing is, that's a reference for ICP plasmas. So it's very hard to use something else. So we reproduced it, and we found results that were quite close to what Jérôme Brenin was measuring with Valéry Godiac himself when he was in the lab. The idea, if I can recap it with the slide I'm sharing, is that you run your setup without plasma, and you look at the current that is in your coil, depending on your power you input. That's the blue points I'm showing, and you consider that this power will be lost anyway, even if you turn the plasma on. So you make a fit of that. Oops, I'm not changing the slide. You fit this, and you consider it's a lost power, and then when you measure your power, the power you send in the plasma in any other cases, you look at the RF power that is written on your plasma source, and you subtract. You look at the current you have, so that implies that you need to measure the current all the time, which is not something we like to do. But you look at the current and you consider that you have lost current all the time, and that is bringing the power transfer efficiency, which is the ratio on this green curve and the orange curve, around 75 to 80%, or 85. So this order of magnitude, and we were quite confident about it because it's a classical order of magnitude for unmutatedly coupled plasmas. It was the same that was found from Jérôme Brodin, from Pascaline, using previous PhD students using the method from Valérie Goliac. So we were confident with that, and there is no other method in the literature, at least with a better reputation than this one, to characterize the power losses. So I'm quite confident, and still I would be open to recalculate that with an independent method if I could.
Okay. And you assume, I mean, in your model that all the discharge power is going to electrons, it's going yes.
No, that's not what the model is doing. The model is doing a power balance on the electrons, but it's not directly assuming that all the power is going to the electrons. So it's not, we are doing a power balance on the bulk electron. I have quite a painful discussion about this in my manuscript about the approach of Mike Lieberman and the approach of Pascal Chabert, whether you do a power balance on the electrons of the bulk, which was Pascal is doing, or if you do a power balance on the entire plasma, which was Mike is doing. And basically, if you take the good coefficients for plasma voltage, you find the same equations. So it's
yes. And my last comment about that, I mean, when you multiply by 5 your excitation rate, for example,
yes.
What is the difference in the power loss?
Let me find this. So multiplying the excitation by 5 was just it was just a tool I was using because it was easier than to add in some more power sources. I removed this slide. Okay, in the manuscript, the curve I'm looking for shouldn't be that far away. Is the 231, and you can see that so I have around 100 watts. So the high excitation now is 40 watts. So if I'm changing that, I'm moving. Well, no, I'm not multiplying by 3 because that would not make sense. The answer I was going to give you, but I think it's wrong, is just to, so before I changed by 5, the excitation was around 50 watts out of the 150 I was adding in the plasma. And I multiplied that by 5, but that does not mean that now it's going to be 250 watts out of the 150 because the equilibrium is changing. So my fair answer would be to say that I don't know that.
Okay. So, thank you again, and congratulations.
Thank you.
Thank you.
Thank you. So, thanks again for this very nice discussion. And so now, just the other question from the other examiner. So,
Yes. Yes, Denis. Okay, so Denis Packan is in the room. I will probably. Can you hear him? If he's talking.
Maybe we can talk to the computer on my laps and
talk to it.
He will try to fix his mic so that you can hear him. Otherwise, I will repeat the questions.
Repeating the questions may be a good solution. Thank you.
I will see if I can use the computer.
Say this stream something.
Okay, do you hear me?
It's kind of weak.
Wait.
We hear you, but maybe Florian can repeat the question.
Here. Wait.
Yeah, should work now.
Okay. You hear me? Okay. Thank you. So congratulations for your presentation, Florian. It was very clear, and it was very didactic to explain very clearly your point of view. So I really had a lot of pleasure to listen to you and also to read your dissertation. So I'm a bit familiar with what you're doing, not too much, but a little bit, because I was part of your comité de suivi, committee that was following a little bit what you were doing. In any case, I have a few questions. One of them regarding the non-Maxwellian aspects.
Yes.
So you mentioned briefly in your presentation, you went into a little bit more detail in your manuscript about it. So basically what you did is you compare two distribution, Maxwellian and Drewstein distribution. My first question is why Drewstein? Is it in this plasma? Is it expected it's going to be that way or?
No. So maybe I can show the distributions again. So yes, so a Dirichlet distribution will typically is mostly used because you have more electrons at the average temperature and you are cutting the tail. And you know that in the plasma you tend to, the high electron energy tend to be involved more in reactions, so this tail is typically cut. It's also physically an extremum between of the function. A reason for this, another reason I can mention is that this was done in a paper from Gudmundsson, and he was making a continuous analysis of what's happening when you move from a Maxwellian, and you can continuously transform your distribution into a Dirichlet because they are linked physically. So I was considering this as an extremum, as a good example, because you can't really have a distribution going much further to the right like here. It's not something that is expected to be physical. So my understanding is that the electron distribution would be somewhere between Maxwellian and Rubinstein. So so they are both built in different plasma. Maxwellian is when you have thermalized population. Rubinstein is another set of conditions that are in the manuscript. So I was expecting that the electron distribution is somewhere in between. More likely Maxwellian, and actually that's what we measure because we have the EDF with the Large probe. So the idea was to take two extrema for the analysis.
And Gudmundsson, he did his work on the same conditions in terms of plasma? Or?
It was a theory as well, so it was something he did on the global model for chlorine, but so with much more reactions with the excited state, with the vibrationally excited state with different cross sections. So it was a deeper work, but he also studied.
Would it be possible to have an answer by using a code, a Boltzmann code, like for example Boltzig? You put all the cross section and you get some. Would it be possible to do that to find out? Because it might be something else also depending on the condition.
Yes,
right?
yes, I see. I don't see why it would not be possible. So my understanding of this Boltzmann code is that you would freeze the distribution and you will let the code solve it. You will let the code solve it and make output in a distribution. I don't see why it wouldn't be possible. I didn't go in that direction.
Okay. I think if you have that's something that could be done easily, probably by putting all the cross sections that you have, and you see what comes out. That maybe tell you what.
Another interesting answer for that. So, two other comments I can make on this is the first. So we do measure the electron energy distribution function with the Large probe, and we saw that except at some extrema, we are quite Maxwellian, and the extrema we could see them in argon as well. So maybe it's a problem with the experiment. So we are quite confident it's Maxwellian. On the other side, is we show the entire purpose of the part I did is to show that the model is not really depending on the electron distribution function except the temperature. And actually, if we get clear about the model, maybe we could even use the measurements, the electron temperature measurements, to constrain the EDF, because what we see is if I move to the Drievenstein, you see that the peak is around 1 eV further, and the plasma will adjust itself by moving up 1 eV so that everything else stays the same as much as possible.
Well, okay, I have a question about it actually, because my follow-up question is that, because you use Maxwellian, in all your work basically you use
Except in this part I use
Maxwellian.
Exactly the part when I study the influence.
So, and I see that you showed some curves where indeed the results are close between the two, but then if you look at the more basic data, for example, the ionization reaction rate,
yes.
page 105, and you look at the 2 eV, for example, which is some temperature that is typical for you, I think, if I understand. You have nearly 2 orders of magnitude different for ionization reaction rate between Maxwellian and Brewstein.
Exactly.
And I'm wondering why, what is your interpretation of the fact that you have 2 orders of magnitude different for ionization, and yet the rest, I mean, the model basically doesn't depend on that.
Okay, I will show the curve we are talking about on screen. So it's the top reaction, so in the solid curve is the reaction rate that is computed with the Maxwellian, and the dashed line is computed with Drievenstein.
I was looking at the 2 blue curves at 2
yes.
eV, and they're very, very far apart, so I was wondering why there's such a difference here, and in the simulation that you compare a bit later, all the results are kind of the same, the 2. You would think that with such a different ionization, there would be...
exactly. So what we see is... okay, I won't go in show that because it will be... the difference is big because that's where you have the threshold of energy. So you basically suddenly you start integrating the threshold, and this happens 1 eV further if you have Drievenstein and Maxwellian. So you can see it from the curves you integrate. The reason for that. The reason is not changing. That's okay. I will need to. I will show the screen first. So when you have at Maxwellian, you will be around 2 eV. So the physics will bring you here. But when you change with Drievenstein, the plasma will somehow adapt itself so that the reaction rate stays the same because it was in this equilibrium. So that's why you move 1 eV, and the temperature you find. So what you find is all the distribution are all the same because it's the case for all reactions. In most of the reaction, if you shift 1 eV, you find the same distribution as you had before, and that's why that we can see here. It's except the reactions, for example, this one, the dissociative attachment, that they are really limited. In most reactions, if you shift 1 eV, you go back to the situation you had before. So the plasma happens to adapt its electron temperature so that the chemical equilibrium stays the same. So that you have the same densities, you have the same reaction rates.
Because the ionization rate is fixed in your... and that's true if you say, okay, the ionization rate is fixed by some parameter of your experiment that kind of, okay, the ionization rate has to be that value. And so the TE adjusts, or the distribution adjusts so that it has this ionization rate. Is that the case?
No, it does not. We let the system solve itself, okay. And what we see is that the equilibrium, whether we're using one distribution or the other, is at the same point except for temperature. And the reason it's at the same point is that if you move the temperature 1 eV, you find the same reaction rates, which is
why does it move 1 eV?
To adapt itself. You can, well, it's a bit of Darwinian explanation, but it's a...
I was wondering there was like a simple explanation, maybe there is not.
Well, it's the same reason why when you run the model with Maxwellian, I wonder if they see when you run the model with Maxwellian, the equilibrium happens to be here. And I don't have more reason than just it's how the balance is made, because it's that that's the same, no reason for the reason why it's shifted one. The equilibrium happens to be at the same state, and if you so I can imagine it like I did imagine it like way. Like if you have a plasma at equilibrium as a Maxwellian, and everything is fine, and you suddenly change the distribution to go to a Drievenstein, the easiest way for the plasma to keep in equilibrium is to move the temperature up 1 eV, and then everything stays the same.
Or you could change the equilibrium.
Apparently it does not.
Yes,
so that was an interesting point in what we studied. It's like we were surprised about this, and it does not. So well, it still does.
So often there is a reason somewhere, but I was wondering which one there is. Probably is not very obvious.
You can see here we have a factor that is very low, and actually it's only here at the temperature that the ratio is suddenly moving 1 eV up. I don't have much more explanation for that. It's
okay, thank you.
but it was indeed interesting to see that.
Regarding cross sections, quick question. At one point you mentioned there was an uncertainty of, I heard 24%, or did you say? Or 20%?
Yes, that's the absorption cross section for I2. That's a calculation that's been done in 1995, and basically they are saying that the cross section is 150 femto square meter plus or minus 250 femto square meter.
Oh, okay.
And that's the value we have for the absorption cross section. And if you take that, that gets you the
wondering with the 24% or something.
Yeah, that's
weird.
Yes, that's the way. Yeah, that's my reading.
Yes, you at the beginning in your manuscript you also mentioned you have a graph that shows figure 1.9. The global model, I think, which the results which I found interesting, there wasn't really what conditions they were made, if it corresponds to your conditions, because you don't have really the details. Or page
Figure 1.9.
Page 27. No, not too far. Yes. And because they say basically the ion the ionization cost, okay, depending on the temperature for different gas. This is a global model, right? Or
somehow.
To what does it apply? Because this is the result of a model, and in there you have losses, and which losses are in there.
Exactly.
And so is it relevant to what you're doing?
Okay, so maybe I need some more feedback. So maybe I can turn that here. So I'm going to use the whiteboard. So this is built with a notion from Lieberman, saying that when you do the model global for your particle balance or for your power balance, you look at how much ionization is happening, and you say that while you have an ionization happening, you also have elastic collision and excitation, and that makes.
I understand that, but then in your case, the dominant losses are the wall losses.
Yeah, no, that's
in there.
No, that's not taking.
Okay,
so the losses that are there are the excitation and the elastic, and that's why it's so low in I2. Is that we say that I2 that we don't have excitation losses for I2, and that was the reason of my conclusion, saying I would not be surprised that the excited losses, that the losses I'm looking for should be looked for in the molecular phenomena, because somehow I don't really trust this curve.
Yeah,
because it's
too low. It's mystic. Because when I saw that, I said, okay, so we need like a thruster that uses high T, basically. We have a thruster, we have a high T, not 2 eV, but 20 eV. Then you really gain by going to iodine. But then those curves are misleading, in fact. They're not really to be used. They cannot be used that way, because...
I took them as a qualitative interpretation of how good the propellant can be, because it's you still have a measurement of how much losses you will get at a certain temperature. It's true that depending on the plasma you use, the temperature will not be the same, so you cannot use it as drawing a vertical line and see what's happening. But you know that if you had a plasma that would have a curve at the top right, it's probably something you don't want to use. And here we could, that's why this curve is in the introduction and not in the global model bound. But here you can see that iodine plasmas are quite very low on the left, and very low on the very left, which makes them somehow interesting as a first approach. That was a way to quantifying the fact that, it's probably a very good propellant. But the fact that they are so low is because there is no excitation processes in the model. No, they are in the Lieberman model. Just they are not in the ion physics, because everybody is neglecting them, because you assume that because the dissociation energy is 1.5 eV and your plasma is 2 or 3 eV, then all your molecules are dissociated, which we proved wrong. So
that's okay. Thank you for that, and that leads to maybe my last question. What is the dissociation degree in your plasma?
And Well, it's because not everybody has the same dissociation degree. The dissociation ratio I have, which is Ne over Ne2,
Yes.
we show that at the center, not in average, was around 60 to 80%.
And because what I saw is in one of your, because yes, that's one. So my question is the following: in the table where you show the different losses and gains of I and I2, I think the main loss every time is the loss through the hole. Basically, you go through. So no, let me be more clear on that. If you take your box, your thruster, you have an inlet is the iodine in, and the outlet is what goes through the hole. And I saw that the loss through the holes is about, in terms of I2, is 20 times more of iodine of I than I2. And I was thinking, why is there 20 times more loss of I than I2? So I thought maybe because there is no I2, or 20 times less I2 in the plasma, or is it because it's? So I was wondering about that.
Yes, I see what you mean.
It's, let's see, which is it? Page page 86, 88.
So it's figure 226 and 227.
86 and 88. Yes, exactly. 225, you have flux of I2 through the holes is 210 to the 20. And figure 227, flux of I through the hole is 8 to the 21. So if you divide by 2 because it's I, not I2, we find the factor several times, basically.
Yeah, of more of I.
And I was wondering why.
Well, so you have two phenomena that add up. The first one is that you have more I than you have more I2. And the flux is proportional to the thermal speed of those particles, that is the inverse of the square root of the mass. So the I tends to flow, so the I are more and they flow faster outside. So the flux.
It's a square root. Square root of 2, so you have like 60% and 20%. I don't get to the factor 20 or 30 that we have here. So I was wondering, there is some. Is it the ions I plus is accelerated and then recombined, and that makes a higher flux? I was wondering if there was.
No, because so in the model, the ionization stage is completely independent from the ionization stage. So it's the first model of the grid ion thruster when you say that the ions, any particles enter the grid either because they reach the Cs and then they reach the bulk speed and they go outside and then they are accelerated, or they go because of the thermal speed. So in any way, your plasma doesn't see the acceleration stage. So
here it's purely diffusive and
exactly. Okay. I have so on the figure 249. No, sorry, that's not what I did before. So I have a curve somewhere that I can't find where I added on the dissociation degree exactly what you are mentioning. So the ratio, so the gamma E over gamma I plus ratios. I will find it. Okay, figure 220. No, it's the I plus ion over I2 plus ions. I was looking at the dissociation at the number of positive molecules in the. So it's gamma I plus over gamma I plus I2 plus. And you are asking me the question about neutrons. Okay, no, I don't have more explanation for that. I will check the calculation, but just you have more I, and then the density that's coming. I think it's proportional to the exhaust.
Could it be that instead of being 60 or 80%, it's like 95%?
Maybe yes. I need to check. So all the analysis I've done with all those curves when you show are at a single point, and normally I took something that was quite.
So there's no like a special phenomena. It's really
no. Sorry, I get your questions. The models I show is from the ratio I show is from the model, and in the model we have 95 or 97% dissociation.
Ah, okay.
So in the model, that's what I showed. So sorry, that's experimentally. In the model, we see no I2 at all, or nearly no I2.
Okay.
That's one of the first slides. I can show you again the dissociation.
Yeah. So it was the dissociation was overestimated, but I didn't
Yes,
think
but the analysis I do at the beginning is done through by the. So this is a dissociation in the model. So that's I over I plus I2, and it's 80%. That's the model is based on what people like about it's what people like about iodine, because in the model you have no molecules, you have no negative ions.
Okay.
So
okay.
So that's where the order of magnitude comes from. Sorry.
Okay. That explains it. All right. I think that no more questions. Thank you very much, and congratulations again.
Thank you.
Okay, yeah, thank you. The difficulty with this model, but it's very clear.
Sorry, just can you turn on your microphone?
Yes.
Sorry, I can't hear you there. We are waiting for Cyril to turn off the microphone. So now it should work again. Okay, I'm back.
Yeah. Okay, so now the next person who will ask questions is Nicolas Sisourat. Where is the room?
Yeah, no, I'm not to do.
Yeah,
we can hear you.
I'm going to also turn on the camera. Yeah, of course.
I can see you now, I'm not sure.
So first, I would like to apologize for that so far, but I'm stuck in this morning and I couldn't. I would like to congratulate you for this work. It's really impressive that you did theory and experiment, and within the writing, it's your so it's possible. And also on the experimental side, but like the black part, but also what is spectroscopy. And I really enjoyed reading the presentation. Even though I'm a theoretical chemist, you made things pretty clear. Congratulations for that.
Thank you.
I have some general questions first. So, so you have used a lot of spectroscopy, different kind of nodes, and in my field, the standard they move towards coincident measurement. So like you measure electrons with ions or ions with photons and kind of stuff. Did you get anything with that in your experiment? And what kind of coincident measurement you like?
Maybe I can repeat the question. Yes. So the question was about coincident measurements, so using spectroscopy to measure two different plasma things at the same time, if I understood the question right, for example, two densities, two temperatures. In my very case, with Pegas, I never considered this a useful thing because we have a plasma that we are running all the time at a steady state, and we assume that the plasma is not changing from one day to another. So because the main idea we have is that the plasma is always the same, whether I come one day, the next day, I always wait for it to be stable before I start experiments. I did that. We did first I, then I2, then electrons. I took care that to be sure that the setup was always the same. To keep the same grace, to keep the same around the same temperature, to measure the currents and so on. So we did measurements not simultaneously. I can imagine that if we move to, for example, spatially or temporally resolved measurements in another setup, for example, to measure the decrease of I atoms, to measure the dissociation, then it could be a good opportunity to do it, because we cannot assume that we could reproduce exactly the same measurement the next day or the next setup, so that would be a good idea to have the measurement at the same time. But so the short answer is no, I don't think that on my very case that would be helpful, but that could be something to think about when designing a next setup.
But in your case, when you
then it's an experiment with really good spatial or temporal resolutions that I don't have right now. Okay, I see the point.
You give the volume of the gas, and I was just wondering how does it compare with the real cluster? Is it that big, that small?
Well, the question is there is no clear definition of real clusters. So we have Ane Aanesland on the call, and she's working with clusters that can fit in your hand, or we have people that working with saffron in the lab, and then the clusters are some liters heavy. So the cluster we have is the former Pegas cluster. So it was a laboratory cluster. It was never meant to fly, but it was it's a volume somewhere in between the big thrusters and the small thrusters. It's definitely not representative of the miniaturized thrusters, but it's not a big one either. I can, but I think that would take a lot of time. That was one possible field of work at the beginning of my PhD. I did some in the code, so I did not write it in manuscript, but I did some studies. If you change the radius, for example, of your thruster, or while keeping the same form factor, it's interesting because you see first the effect of the pressure changing, but if you correct for the pressure, then you see the effect of the power density changing, but if you correct for the power density, then you start to have the effects of the related surface to volume ratio, which is quite interesting. And it appeared that the scaling laws were not that easy, and I would really anticipate from discussions I have with physicists that the scaling laws would be interesting, but would need some strong calibration before being able to be used. That could be a field of subject for next PhD student.
You also mentioned that you have to take care of corrosion. You have to clean well everything such that it doesn't mess up the whole.
Yes.
How would you do that in a real cluster? There would be no one cleaning there. So, any idea how that would be?
Yes. First, I can't resist the opportunity to show you some of the backup slide with pictures. Yes, sorry. So the middle part here, you see, it's what's deposited in the iodine trap after the trap. So it's a big layer of crust of iodine that we need to clean every day, and because otherwise it vaporizes again and it's becoming a source of I2. Let me go back to my setup. The problem with iodine deposition for me is first for the pump. So okay, the pump you can't see because of the. So here is the full slide, but you probably remember it. At the bottom you have the pumps. The first problem is for the pumps. So the iodine would solidify in the scroll pump, and before even talking about corrosion, the fact that we have granularity and we have this kind of dust, this is what would damage first the pump. So we need to clean, not because of the corrosion, but just because of the fact that we are recreating dust or grains. So that's the first problem. It's more a problem of dusty plasma than a problem of corrosive plasma. So we are already taking care for the pump. We are taking care for the environment because we don't want it to go in the environment because it would damage the water or it's bad for the environment. The deposition happens a lot in the chamber, and we need to take care of the chamber. That when you deposit, you need to clean before you open because it's the conjugation of deposition and opening to open air that will start the corrosion. And so you see where I'm going on. In space, you don't have all these downstream parts. So you don't have a problem of pump. The natural pump of space is not going to be a problem with your solidification. You don't have the vacuum chamber to have a problem with. So the problem in space are more the ionization chamber itself, but then the plasma has a good way of cleaning the surfaces you work on. But it's a matter of finding you still have a matter of finding the good materials, and I know it's an active field of research in some of the well-known startups working on iodine plasmas. And then you have a huge problem of clogging. So when you have deposition in the injection lines, and it's something they studied at NASA. It's in the NASA Air Force lab. When they show So it's a problem we have. If you, for example, here the pipe is heated at 95, and if you stop this heating, you will start to have iodine accumulating. The iodine, by principle, is accumulating everywhere it's colder. So you want the coldest parts to be the source. That's why the source is 90 when the pipes are 95. And they show that you can have some good procedures if you reheat your system, then it can work again. Because in the meantime, you won't have the connection to the contact with water or the contact with oxygen that is bringing you the corrosion. So iodine is not that a problem if you remove pumps and if you remove air, basically. And that's two things you have in space quite easy. So it's still an engineering challenge, but I know it's an engineering challenge being tackled because you have some thruster like this on the market, and it's still slightly easier, I feel, than to work in the lab because you have less things to take care of.
Usually suspected depends strongly on the extent of pressure, so that you have collisions and so on. Do you think you have clusters in your chamber? Like several iodine molecules together or something? Or do you think you can assume that it's only isolated species?
First comment on this, the part that is depending on collisions I'm not using for my spectroscopy because I'm not able to understand the redistribution of the optical saturation that is happening in this case. Otherwise, I think I'm way below the order of precision you are asking me here. So I'm not I'm working on volume averaged on plasma population. So I'm not able to tell you, and I've never been interested in knowing exactly where was my molecules and whether the molecule was isolated and making a cluster. We have had some tricky questions about whether we have a flow, for example, in the thruster, because that would change the behavior of the gas. That's a question we have. I never thought about the question you ask. I'm not sure from my non-chemical background how it would change the physics, but so I don't know about this.
Well, the cross-section would be completely different for any processes, so then you would have to include cross-section everything.
Okay, because it would be equivalent to a I4 or I6 molecule in some ways, because you would
be similar.
Similar, yes. Okay. Yes, it would be equivalent to having more species if you have some.
As far as the global model. There are more technical questions. You use longer probe, and you show that when you move it, we don't have the same output, so it shows that you have some kind of distribution.
Yes.
I was wondering if your probe itself affects the plasma. Because it's not like you become where it's non-intrusive and you know that you don't capture the
Yes.
the longer probe is good, right?
Yes, and it does. Because I just want to show again. Yes. So I'm going to put. So I'm showing the slide 130 again. I will remove. Okay, you can see everything. So just as a matter, the light blue curve, which is the most gradient, is at 4.5 Pascal. So at the point we take, so at 0.2, 0.3 Pascal, we are at the curve at the bottom. So the gradients are way smaller. The problem is still the same because we don't know if we have a symmetrical distribution or not in the plasma, so we can't assume anything about the average or the center value. But so, and the second part of the question is about whether the probe is disturbing. Yes, it does. That's the main idea of long view probes. If it's quite easy to implement, it's rather easy now to analyze, but it's disturbing your plasma. Whether the laser setups so the long view probe experiment was a couple of weeks when the laser experiment was a couple of months. And it does disturb the plasma. It's creating a sheath around. There is a sheath around the probe that is attracting more ions. So the idea is to you take that into account when you do the analysis, And the idea is taking a probe as small as possible, and we saw that the probe tip, what is doing exactly the measurement, is 3.9 millimeter over 200 micron in diameter. It's never small enough for plasma physicists, but it's something that is starting to be very small compared to all the relevant typical length in the plasma. So that's how we are limiting the disturbance. But of course, it's disturbing the plasma, and we need to take that into account. The next probe we are building with Benjamin is with 100 micron tungsten wires, so it will be even better. And the probes from Jérôme Brenin that we couldn't replicate were actually surrounding those tungsten wires by quartz filaments, this 300 microns, and then adding one smaller 20 microns, I guess, filament in the middle, and this 20 micron tip would do. But then it's like it's jewelry with quartz, and it was something we didn't do again. It was basically his PhD, and we didn't want to take 6 months building a probe. Is that a so you said that the spin orbit coupling is not taken at all in the calculation. Is it a question or an affirmation?
It's not a question. This is I'm pretty sure I look at it.
Okay, I'm happy that it's not a question. Okay, interesting.
So the question is, do you think it's important to include it somehow, at some point? You discuss with them if they could do it, or do you think it's just not going forward?
For the cross sections.
Electronic part cross section.
I don't know. I'm afraid we are getting out of my field of expertise on this. I know that the team from Timo is doing everything they can to get the best data. So if they didn't take that, it's either they feel it was not relevant or too complex. But I don't have any satisfying answer for this. It's out of my field.
I don't know either. I was wondering, actually, discuss with them. As far as I know, something
no, that's a work that was being done just before I arrived by Ane Bourdon and Romain Luquen mostly. So maybe Romain would have more information about this because he was the one in contact with Timo. So maybe he could answer that, but I can't.
You also show in the model that for combination of the wall is very important. So you have to add uniform
Yes.
molecules. As a quantum chemist, this is the kind of stuff that are quite important to compute. Now I was wondering what kind of, I would need a model first of all. Like,
Yes.
what would be, what should we put at the surface of your wall, like iron, carbon?
So in theory, so what I have here is anodized aluminium. I'm not sure what it's anodized aluminum. I'm not sure what people doing real thrusters are using. But if we can cross-check your measurements in our setup, it would be good.
So I would take like just the surface of aluminum atoms and see how
That's the thing. One thing I'm expecting is that the wall is not really staying the same a long time. That's the reason why we didn't do the experiments about scaling in the thruster. Is that one of the ideas we discussed with Ane in this case is that we could add some dead volume inside the plasma, for example, a layer of 1 centimeter of anything inside to reduce the volume. But there would be no way that I have, except redoing the thruster every time to ensure that the surface we add is the same kind of the thruster we had before. So I wouldn't have been able in the data analysis to tell you, okay, this effect comes from the fact that we reduce the volume, or this effect comes from the fact that we just changed the walls completely. So what we did was to assume that if the wall surface was not changing over the course of a few weeks, And that's why when we do the experiment when I did the experiments, we considered that it did not change, but I cannot assure you that the walls I have now have the same physical structure that they were when they were built 5 or 6 years ago. But if you are confident in the measurements, I mean you as a community, I don't really know how the calculations are going, then maybe it's a good reason to do a new thruster in the good material to be able to compare directly with your calculation.
I have a question on your code, or how to do it. So you solve your differential equation until you reach equilibrium.
Yes.
How long do you have to propagate to reach equilibrium? I mean, in the plasma reduce, release the power, how long it takes for all the reaction to equilibrium?
A few milliseconds. It's so I've solved until 1 second just to be sure, but I have a dynamic time step. A dynamic time step, so basically everything is converged around 1 millisecond. So the code from Pascal was stopping at 1 millisecond. I extended that to be sure to catch some of the, because I was doing some parametric analysis, so the initial case I was using was not always very relevant for what I was measuring, so I extended it to 1 second, but it's a millisecond range.
And how long did it take to do it? I mean, time this time?
For anything we do code, nothing. I have the numbers here. So that's screenshots of my manuscript that I use in this slide. So here are the numbers when I was running the Monte Carlo simulation. So it was running on the pool of, and we are at 0.3 seconds for one case. No, sorry, that's with 64. So it's milliseconds as well, even to run. It's hundreds of milliseconds. So yes, so sometimes the code took 15 minutes to run, but it was running for 100,000 cases, and it was so that was the most complex. So actually, it's quite good CPUs. It's a small machine we have in lab, but compared to the big codes we are doing in lab, everything is basically immediate, except when you are running 100,000 of them.
Okay. And last question on the comparison between the model and the measurement. So you discussed this combination factor at the wall, so you have 0.1 or 0.5, and your conclusion is that 0.1 is better than 0.5 because of the trends.
Yes.
Of the result. But if you look at, to me, looking at the result, it seems that the agreement quantitatively is better with 0.5. You always get closer. The trends are not right, but why the trends are more important than the quantitative? For example, this one, but it's also true in many
Yes.
Get result in the back.
I wouldn't say that the trends are more important. I would say I believe my trends more than I believe my actual values, because it's so here, for example, these values are the line integrated measurements. So I'm taking the absorption along the line of sight. So it's integrated over the structures, and as we saw at this kind of pressure, it's not necessarily homogeneous. And so the first model I did to get the center value was to suppose a cosine distribution, for example. So you suppose a cosine distribution, so the value of your center is pi over 2 times your average value. So but if you change the cosine distribution by saying you have some recombination, then it's not 0 at 0, you would change. What I mean, it's very easy to add a multiplicative factor to all your data, which means that the absolute value, I could easily find a factor of 2 here. But if I wanted, I think I can find a factor of 2 somewhere in the model, in this 1D model, and I can say, okay, we are fitting exactly what we want. I'm not completely sure about the complete value, but what is sure is whether we are talking about line integrated values, center values, for I, we always find something linear with pressure. So that's why I'm trusting more the trends here than the actual values. It's not exactly the case for I2, for example. For I2, because the measurements with the center measurements need both the line of sight integral and the external measure of pressure, you start to have more uncertainties, and then I wouldn't have the same speech. But for this one, I definitely trust more the trends. could be done, but I feel that the parameter space to do that is still too big before we can study more.
Yeah, but you have so many probes that maybe we don't cost.
I wouldn't say I have so many probes compared to what they use in so many other gases, but that's what I try to do now here. It's like to compare measurements from different sources
Yeah, but I mean, doing quantitatively, because now
yes.
it's on quantitative, which is also just study.
Well, it's quantitative way in a way that I'm using, like this data is saying that gamma is probably very small, but it's also saying that we are lacking high density. We have too much high density in the model, so that the dissociation is underestimated. So I have also some quantitative measurement as well, but I see your point.
Oh, I think I'm the question of calculation again. Nice to meet that.
Thank you.
Okay. So thank you very much. So I think that we're very very appreciative of how students can like very interesting discussions. Guarantee of the quality of the work. And now there is no more internal question, but
I think we can't hear you anymore. You are repeating. Yes, the voice is.
can you hear me now?
That's better, yes.
So I was saying that now the external referring questions are over, and instead for Ane Aanesland will actually either ask a question or just comment on your work. So Ane, are you there? Can you hear me?
Yep, I'm here. Thank you very much. Yeah, thank you very much. So, congratulate you for the presentation, the thesis, and the work that you've done. Would also like to apologize for suddenly disappearing in the beginning of your thesis. So, for those that are not aware, when Florian started PhD, it was during the time when I decided to jump off the research for a while and trade the company in. And of course, during this time, you tend to put your notepad, but that only happens for hours a day. So Florian was to follow stuff for me and I was really
Sorry, Ane, sorry, Ane, maybe if you turn off your camera, we will hear you a bit better. Ane, we have trouble hearing you. Maybe can you turn off your camera? It seems to be better. Maybe if you speak a little slower, it's less clear.
Yeah, so what I wanted to say also in addition to thank Florian, I would also like to thank all those that have contributed when I left. So Cyril, Ane, and Pascal that have day-to-day followed you and supervised you during this PhD. And what you can see is that also your PhD is not exactly what we had in mind when we started out. So it's very interesting what you've done. I think that there is many questions that you are opening. I have many questions for you that I will not ask them today. I would really like
Thank you.
Thank you, Ane. So next, Dr. Drag.
Yes.
Thank you. I'm moving next to the source of the head.
Thank you. So, and maybe 5 minutes in French. This presentation. Bien, donc moi j'ai travaillé avec Florian un peu par hasard. C'était en fait une rencontre scientifique comme il peut avoir lieu dans les laboratoires parce que au moment où j'arrivais, Florian avait commencé sa thèse. Et le premier point qui m'a beaucoup plu dans le travail avec Florian, c'est que c'est la curiosité qui l'a amené à travailler avec moi. Parce qu'en fait, lorsque je lui ai dit que je disposais d'une cellule d'iode dans laquelle on pourrait faire un plasma, qu'on enverrait un laser, qu'on allait sûrement voir des choses sur les atomes et molécules des ions, il était très enthousiaste et nous avons commencé à travailler comme ça. Ce n'était pas évident, car Florian avait fait plusieurs mois de calcul dans son bureau. Et par exemple, la première fois que je lui ai demandé si un laser était éteint, son réflexe a été de mettre la main dans le faisceau, alors que c'était un laser de 10 watts de puissance verte, et il aurait peut-être pu perdre un doigt. Bon, peut-être pas. Toujours est-il que cette phase d'expérience m'a montré que Florian était un thésard qui avait énormément de ressources, énormément de connaissances fondamentales, en physique, en mathématiques, et qui était très efficace pour mener à bien des expériences. Et c'est lui qui ensuite a décidé de reprendre les manus sur pliage et de mettre en œuvre des diagnostics optiques originaux afin de les comparer avec les nombreux calculs qu'il avait menés auparavant. Et ce qui était intéressant dans sa démarche, c'est qu'il a fait à la fois l'expérimentateur et le théoricien, alors que des fois ce sont des communautés séparées. Et comme vous avez pu l'apprécier, il a mené le plus loin possible. Il a bien vu les limites de ses outils, les limites de ses modèles, les limites de ses mesures, mais il a su mener le plus loin possible ses travaux. Et, comme a dit Ane aussi, avec différents collègues au laboratoire, Jean-Paul Bousse aussi, Anne Bourdon et Pascal Chabert, qui ont participé aux discussions scientifiques. Je finis sur l'aspect science en 30 secondes pour dire qu'une grande qualité qui m'a toujours impressionné chez Florian, c'est que je le vois comme un génie du code Python. Alors peut-être que mon niveau est très bas dans ce langage, mais j'ai beaucoup aimé les après-midi ou durant les séances de travail, lorsque j'essayais de débroussailler un problème au tableau ou avec une feuille de papier, et que toi, pendant la conversation, tu étais en train de coder ça sous Python, et à la fin de la conversation, tu disais, tu peux arrêter, nous avons le résultat à l'écran, et c'était très intéressant. Donc ça, c'est l'aspect science. Je voudrais dire 2 mots aussi sur tes qualités humaines. Donc, je voudrais déjà rappeler que tu étais employé 4 heures par semaine, c'est ça?
6
heures par semaine pour encadrer le centre spatial étudiant. Et donc, durant cette période, en plus de ta thèse, donc, tu encadrais une dizaine d'étudiants, je pense. Et le but, c'était des gens qui découvraient la propulsion, donc à travers des projets, et ils arrivaient sans rien connaître à la propulsion, et en fin de leur année d'études, pouvaient dimensionner un satellite et même aboutir au lancement, je crois, de différents cul-de-sac. Donc c'est une activité que tu as eue. Et je voudrais finir aussi pour noter que tu as eu un rôle quand même important sur la vie sociale du laboratoire. Je pense que tes collègues ne démentiront pas que tu étais un peu le chef des thésards pendant cette période et cette promotion, et tu as été à l'origine de l'organisation de nombreux événements festifs, scientifiques, et que tu as toujours pris en main des postdocs qui arrivaient, ou des stagiaires, que ce soit de niveau L3 ou L1, et tu voyais un étudiant un peu perdu dans les couloirs, c'est toi qui contribuais à l'intégrer dans le laboratoire, et très souvent à t'occuper de tes collègues. Et donc, en résumé, pour toutes ces qualités quand même scientifiques, humaines que tu as, j'ai beaucoup aimé travailler avec toi durant ta thèse. Voilà. Félicitations.
Okay, so Florian?
Yes.
So just to let you know, the jury was very impressed by the amount of credit. We appreciated the effort in the presentation. It was very logical and appreciated by everybody, and reflected both experimental and theoretical work. So I look forward to this. we thought that both the presentation and the question showed that you acquired a broad knowledge and a scientific maturity, giving pioneering contribution in a new field. You showed to be at ease also, and you have some able to adapt to initial change in the thesis director. You answered the question in an independent and personal way, so this resulted in a nice scientific discussion, and so for all these reasons we congratulate you, and I declare you PhD Doctor in Physics at the Sorbonne University. Congratulations.
Congratulations. I think if you want to say a few words, I think it's your time now. It's already.
I think the connection is weak. You just say a couple of words,
Oui.
and then I have, so the connection is very nice, so just you want to say something.
Ok, en français peut-être. Merci beaucoup à ceux qui sont là en ligne et dans la salle. Merci au jury d'abord d'avoir réussi ce challenge, enfin d'avoir accepté et réussi ce challenge de la soutenance en visioconférence. C'était pas évident ici, donc je suppose que c'était pas évident forcément pour vous ailleurs. Merci à mes encadrants successifs, donc Ane, enfin mes encadrants tout court, Ane, Ane, Pascal, Cyril, merci beaucoup pour, c'est grâce à vous que je suis là aujourd'hui devant cet écran. Merci à Marine qui a géré la visio, à Inès, Antoine sur le chat, à Philippe pour toute l'aide technique pour mettre en place la visioconférence, à tous les gens du labo qui sont peut-être qui sont pas dans la salle mais qui sont peut-être sur le live et en tout cas qui seront au cocktail, j'en doute pas dans quelques minutes. Merci à tout le monde pour ces donc 3 ans et demi, 42 mois au LPP. Voilà, finir sur le Covid, enfin, ça aurait pu plus mal se finir avec une visio complètement, une thèse complètement en visio, c'est cool de pouvoir avoir des gens dans la salle aujourd'hui. Merci beaucoup pour les discussions scientifiques et pour la thèse en général. Voilà, merci.
Okay.